Before airplanes became the safest way to travel, a small design mistake changed everything. Most people never notice it, but airplane windows weren't always round. Title: Why Plane Windows Are Round. Opening hook: the failure that changed aviation. In 1954, two brand-new jet airliners fell out of the sky, not because of pilot error, not because of engine failure, but because of their windows. The aircraft was the de Havilland Comet, the world's first commercial jetliner. It was sleek, fast, revolutionary, and it was tearing itself apart at 35,000 feet. Visual: black and white footage of early jetliners taking off. Cut to wreckage recovery in the ocean. Investigators recovered fragments from the seabed and rebuilt the fuselage inside a hangar. What they found was unsettling. Cracks had formed at the corners of the cabin windows. Not in the wings, not in the engines, in the windows. On paper, a window is just a hole in a metal tube. But at altitude, that hole becomes the most dangerous feature on the aircraft. And to understand why, we need to start with first principles. In the early days of commercial jet travel, speed was everything. Part 1. The context. Why we pressurize aircraft. At sea level, the air around you weighs about 101 kilopascals. That pressure is not abstract. It's the weight of the entire atmosphere pressing down on every square meter of your body. At 35,000 feet, that pressure drops to roughly 23 kilopascals. That's less than a quarter of what your body expects. Visual: graph of atmospheric pressure versus altitude. Without pressurization, passengers would lose consciousness in seconds. So modern aircraft maintain a cabin pressure equivalent to about 6,000 to 8,000 feet. That means the fuselage must withstand a constant pressure difference of roughly 8 to 9 psi. It doesn't sound like much, but multiply 8 psi across the surface area of a wide-body aircraft, roughly 700 square meters. That's millions of pounds of force trying to burst the aircraft open. Visual: animation of fuselage cross-section expanding under pressure. An airplane at cruise altitude is essentially a pressurized aluminum cylinder. And cylinders under pressure obey very specific physics. Part 2. The physics constraint. Stress concentration. When you pressurize a cylindrical fuselage, two main stresses appear. Hoop stress, circumferential. Longitudinal stress. The hoop stress is roughly twice the longitudinal stress. The equation looks like this. Sigma equals P times R / T, where P is pressure difference, R is fuselage radius, T is wall thickness. This equation tells us something important. Stress increases with radius. Stress decreases with thickness. But increasing thickness adds weight. And in aviation, weight is fuel. Fuel is cost. Cost determines viability. So engineers operate at the edge of structural efficiency. Now here's the problem. A smooth cylinder distributes stress evenly. But the moment you cut a hole in it, everything changes. Visual: finite element analysis of smooth tube versus tube with square cutout. At the corners of a square opening, stress doesn't remain uniform. Concentrates. This is called a stress concentration factor. At a sharp corner, the local stress can be 2 to 5 times higher than the average stress. And metal doesn't fail because of average stress. It fails at the maximum stress. Part 3. The Comet Disaster. The de Havilland Comet had large, square windows. They looked modern, architectural, clean, but they had sharp corners. Each flight cycle, pressurization and depressurization, acted like bending a paperclip back and forth. This is fatigue. Metal fatigue is governed by crack propagation. At the microscopic level, aluminum contains tiny imperfections, dislocations in the crystal lattice. Under cyclic loading, cracks begin at stress concentration points, and sharp corners are perfect crack starters. Visual: microscope-level animation of crack forming at corner. The Comet underwent repeated pressure cycles. Eventually, cracks grew large enough that the fuselage tore open explosively. This wasn't a materials failure. It was geometry. So next time you look out of an airplane window, remember, that shape saved aviation. For more insane aviation secrets explained in 60 seconds, Subscribe now and don't miss the next one. Part 4. Why round works. A circle has no corners. That sounds trivial. But mathematically, it's everything. In elasticity theory, the stress concentration factor for a circular hole in a uniformly stressed plate is exactly 3. And crucially, it is evenly distributed. No singular spikes. No infinite stresses at corners. It was revolutionary, fast, futuristic, and it had square window. Visual, stress distribution heat map of circular versus square window. Why? Because curvature distributes force continuously. A sharp corner has near zero radius of curvature. That means stress approaches infinity at the tip, in theory. In practice, that means cracking begins there. A rounded window spreads the stress flow lines smoothly around the opening. Think of water flowing around a rock versus a brick. The rock produces smooth streamlines. The brick creates turbulence. Stress behaves the same way. Part 5. Materials Science Angle. Primary focus. Let's zoom in further. Aircraft fuselages are typically made from aluminum alloys like 2024 or 7075. These alloys are chosen for high strength-to-weight ratio. But aluminum has no true fatigue limit. Unlike some steels, which can theoretically survive infinite cycles below a certain stress threshold, aluminum will eventually crack under repeated loading. So engineers must minimize peak stress. Every reduction in stress amplitude dramatically increases fatigue life. Visual SN curve, stress versus number of cycles. For aluminum, a small increase in peak stress can reduce lifespan by orders of magnitude. That's why geometry matters more than raw strength. You can't just make it stronger. You must design it smarter. Part 6. Why not just make the fuselage thicker? Because weight compounds. Every extra kilogram requires more lift. More lift requires more wing area or higher speed. Higher speed increases drag. Drag increases fuel burn. Fuel adds more weight. This is the tyranny of aircraft design. Everything is connected. Adding 1 kilogram structurally may require 3 kilograms more fuel over an aircraft's lifetime. So instead of brute force thickness, engineers optimize shape. A rounded window adds almost no weight, but dramatically reduces stress concentration. It's an elegant solution. Part 7. Multilayer windows. Modern aircraft windows are not just holes. They are multilayer pressure systems. Typically, outer structural pane, middle failsafe pane, inner cosmetic pane. The outer pane carries the load. The inner pane exists to protect against scratches and passenger contact. There's also a tiny bleed hole in the middle layer. Visual. Exploded view of aircraft window assembly. That hole ensures pressure equalizes across the correct pane. Without it, load distribution would change. Even the size of that hole is engineered, because at altitude, pressure differentials are relentless. Part 8. Why they're small. Another common question. Why not make windows larger? Because stress scales with area removed. A larger opening weakens the fuselage more. Every centimeter added increases reinforcement requirements. Reinforcement adds weight. Again, trade-offs. That's why aircraft like the Boeing 787 Dreamliner use larger windows only because composite materials allow better fatigue resistance and tailored reinforcement. But even those windows are rounded, because physics hasn't changed. Part 9. Composites change the game, but not the rules. Modern aircraft increasingly use carbon fiber reinforced polymers. Composites resist fatigue better than aluminum. They don't suffer crack propagation in the same way. But they introduce new problems. Delamination, matrix cracking, impact sensitivity. Visual, carbon fiber layer stack under load. Even in composites, sharp corners concentrate stress in fibers. So designers still avoid square windows. Not because tradition demands it, but because stress concentration is universal. It doesn't care what material you use. Part 10. Economic reality. Airlines operate on razor-thin margins. A structural redesign costs billions in certification, testing, and tooling. A new window shape must survive. Tens of thousands of pressurization cycles. Bird strikes. Temperature swings from -50 degrees Celsius to cabin warmth. Certification testing includes pressurizing fuselages inside giant water tanks repeatedly until failure. Visual. Fuselage pressure test in water tank. It's expensive, which means solutions must be simple. Round windows are simple, cheap to manufacture, easy to reinforce, proven over decades. Part 11. Debunking the myth. Some believe plane windows are round for aerodynamics. They're not. At cruise speed, airflow barely notices the window indentation. The dominant concern is internal pressurization. This is a structural problem, not a drag problem. Part 12. The verdict. Round windows are not aesthetic. They are not tradition. They are the inevitable outcome of pressure vessel physics, fatigue behavior of metals, weight constraints, economic optimization. The laws of elasticity dictate the shape. If you pressurize a thin-walled cylinder and cut a hole in it, that hole must be round, or it will eventually fail. Final thought. Engineering is rarely about making something look good. It's about negotiating with nature. The comet taught us that physics always wins. Today, every time you look out of a rounded airplane window at 35,000 feet, you're looking at a lesson written in metal fatigue. A reminder that even something as small as a corner can bring down an aircraft, and that the limits of geometry are not suggestions. They are laws. So next time you look out of an airplane window, remember, that shape saved aviation. For more insane aviation secrets explained in 60 seconds, subscribe now and don't miss the next one.